I am going to introduce Rachel Smith. And so Dr. Rachel Smith is the head of the Astronomy and Astrophysics Research Lab and the curator of meteorites at the North Carolina Museum of Natural Sciences. She is also an associate professor at Appalachian State University and an adjunct professor at UNC Chapel Hill in the astronomy department. So she is very busy all the time and does this thing a lot. Amazingly, Rachel, you have time to be here with us and give
really cool I just sit here at my computer all day. That's what we do.
She's always giving amazing presentations. You might have seen her at
thank you, Miranda.
Always interesting. And you're giving one tomorrow?
Yes, I'll be speaking tomorrow on, so Caleb's going to tell us about the giant planets today, and I'll be speaking about the terrestrial planets and asteroids and comets and meteorites tomorrow. So if you come to both, you'll have the entire solar system in your mind. So please do it.
Awesome. So Rachel is going to introduce Caleb for us.
Okay. So thank you, Miranda, for that kind introduction. So Caleb Keaveney, I'm introducing him because he was my intern this summer, and his project was using OpenSpace software, which is the software that he's going to use today to show you and tell you about the giant planets. And I'm not sure if any of you came to the 10 a.m. talk today or have seen OpenSpace before. It's all free software, and we can put the link in the chat, and I can do it if someone doesn't have it. But basically, everything you see is based on real data. I just want to say, and this is a NASA-funded project that we are partners with. The museum is partners with the American Museum of Natural History in New York that has been able to fund this through NASA, and now it's in its 6th year of funding. So everything you see has been built up over years of beta and developers and lots of people being involved. And so Caleb was an intern working with OpenSpace, and he's also, I'll give you a brief intro for Caleb in addition to that. So he is a student, and I just want you to remember that he is a sophomore, so be very nice to him, please. He is a sophomore at NC State. And his major is meteorology and mathematics, which is really super interesting. So you may see him on the news someday as a meteorologist, who knows? He's interested in planetary science, as you can imagine, and especially the atmospheres of giant planets. So that's what his focus, he chose this focus for the program. And he's worked with researchers studying the distribution of volcanoes on Venus and conducted an independent study on the dynamics and chemistry of giant planet atmospheres. This spring and summer, he'll be working on the dynamics of Jupiter's atmosphere more in depth. And I just want to say, I congratulate him because he got an internship this summer working with a scientist at JPL, the Jet Propulsion Laboratory in California, which unfortunately is all virtual, but still it's going to be, I think, a really great experience for him. He's going to use data and do some more analysis on the science of the giant planets. He's actually been interning and volunteering at the museum since he was 14 years old. So he's got some street cred there. And so I will stop talking and let Caleb take it away and tell us all about his giant planet tour. So thank you, Caleb. And please start your program.
All right, well, thank you. So as Dr. Smith mentioned, my name is Caleb, and I'm gonna be talking about, for the most part, the giant planets. But of course, we don't live there, we live here. So if you're looking at my screen, you can see Earth, which is a terrestrial planet. So terrestrial planets, which I believe Dr. Smith is doing a program about tomorrow, for all intents and purposes, are rocks. Or collections of rocks. So we happen to live on a very important rock. Our rock has a lot of water, which is why it's blue. And all of that water drives our atmosphere. And so we experience our atmosphere as weather. And so I'll just mention something really interesting about our atmosphere, which most people I'm sure have heard of, which are hurricanes. So what you're looking at right now is the imaging from September 14th of 2020. So a few months ago, we had a really cool thing happen, which was there were 5 hurricanes, or at least pre-hurricane storms, in the Atlantic Ocean at the same time. So over here on the left, I can zoom in a little bit. What you're seeing here is Hurricane Sally over the Gulf of Mexico. And then as we move east, we see Hurricane Paulette over Bermuda, which is off the coast of the United States. And then this cloud formation here is Tropical Storm Rene, or the remnants of Tropical Storm Rene. And then we have the development of what will become two tropical storms, Tropical Storm Vicky and Tropical Storm Teddy. And tropical storms and hurricanes are probably the most extreme weather event that happens consistently on the Earth. And of course, weather events are things that happen in the atmosphere. And so when we're thinking about weather, of course, we're thinking about the atmosphere. And so it's a natural question to ask, what would happen if our atmosphere was bigger? Or what would happen in the case of the giant planets if we got a planet that was almost entirely atmosphere? And so as you can imagine, given that Earth has a very thin atmosphere and can produce 5 huge storms in the Atlantic Ocean at the same time, we can get some really crazy things happening on the giant planets. And so we're going to go ahead and take a tour of those. So as we head over there, just for clarity's sake, when we're talking about giant planets, at least in our solar system, we're talking about 4, Jupiter, Saturn, Uranus, and Neptune. And they're the 4 biggest planets, of course, the giant planets. And so the first one, of course, is Jupiter. Jupiter is, as we saw earlier, the favorite giant planet. It is the one that we have the most data about. We know the most about Jupiter, and it is the biggest. It is a beast of planets. It is 2.5 times more massive than all of the other planets combined. It could fit every single planet inside of it, including Saturn with its rings. It is a massive body, and it has some really crazy things happening on it. So, of course, the first thing you notice when you look at Jupiter is the Great Red Spot, which is a big red spot because scientists are fantastic at naming things. We'll see several different great spots as we go throughout the tour of the giants. So the Great Red Spot is similar to what we just saw on Earth. So we just looked at hurricanes, and the Great Red Spot is just a hurricane that spins the other direction. So on Earth, hurricanes spin counterclockwise. On Jupiter, this spins the other way. And it is a storm. It is when this picture was taken, it was about 3 Earths across. So it is a huge storm. Winds can get up to 400 miles an hour or a little bit over it. So for context, the fastest winds we've ever experienced on Earth are 230 miles an hour. So nearly twice as fast. And unfortunately for people like me who think these storms are really cool, the Great Red Spot is shrinking. So at its biggest, of course, it was like 3 to 4 Earths across. That was in the late 1800s, early 1900s. That was the biggest. We first observed it in the 1600s. So it could be older than that, but that's when we first observed it. So it's about 400 years old. And it peaked at around the 200-year mark. And since then, it's been on a little bit of a decline. So it's now, as of 2017, a little over 1 Earth across. So we don't really know why it's getting smaller, and we don't know what's going to happen to it. There are a lot of studies right now trying to figure out what the future of this storm looks like. But as of right now, we don't really know. We also don't really know why it's red. So these are some simple things about the storm that we don't really know. So our best guess as to why the red spot is red is because this is a really huge storm. And as you can imagine, a really huge storm is going to create some disturbances lower in the atmosphere. So we think maybe this storm pulls up material from lower in the atmosphere, and some chemical reactions happen, and you get this red color. But we don't really know. So that's something that, again, many studies are looking at, and hopefully we'll know before the red spot maybe dies out. But the good news is, even if we're losing the great red spot, which who knows, the red spot may rebound, given that we don't know why it's been around for 400 years. It could be around for another 400 years, who knows. But even if it did disappear, we have a new storm to get excited about. So I'm just going to turn off the shadows really quick because I have that power in OpenSpace. And we're going to head over to the other side of Jupiter, the night side. And this right here, there's another storm that we can look at. So actually, there it is. So this is a big, another big storm that's forming. Actually, it is bigger than this, and it is a different color from when we first took pictures of it. So the imaging that OpenSpace uses as of right now is taken from the early 2000s. This storm formed in the early 2000s. So we're seeing right here a very new storm. And it formed from 3 other storms coming together, colliding, and making one big one. So if we come back over here for just a second, we can see 3 ovals like this. So of course they're ovals, so we call them ovals. But these 3 storms, these are 3 storms that are examples of what we call white ovals. And 3 white ovals like this collided, made a bigger storm. And we call it oval BA, which is just, it's the scientific name. But we also call it red junior because it's smaller than the great red spot, but it looks similar, at least now. In about 2005, late 2005, early 2006, this storm turned red. So it went from being just this white oval, this big white oval made from 3 smaller ovals, to being a new red spot. And what's really interesting about this storm is it moves around the planet. So the great red spot is stationary, but this storm moves. It's pushed around by the winds in the atmosphere, and it actually circulates and moves around and passes the great red spot. So for a while, we thought maybe that these 2 huge storms would collide, in which case, there were lots of studies trying to figure out what would happen if these 2 huge storms collided. But they didn't, and they probably won't. They could, who knows, but probably, given that they haven't so far, they probably won't. And one of the cool things about storms like this, they tear up a lot of turbulence behind them. So you can see these like wavy patterns behind this storm. And then there's also wavy patterns behind the great red spot. So those are 2 discrete features on Jupiter that it'll be interesting to see what happens to them. So all the more reason to keep pointing our telescopes at Jupiter. Who knows if the great red spot is going to disappear. We don't know how big oval BA is going to get, or I should say red junior. But yeah, so those are 2 really interesting discrete features on Jupiter. And if we come out and look at Jupiter broadly, we can see these stripes. So Jupiter is one of 2 planets that has stripes in our solar system. The next one we'll look at, Saturn, also has stripes, although they're less obvious. And so for a while, me being a nerd about astronomy, unfortunately, I didn't know what caused these stripes until I started looking into it. It's actually really interesting. So these are called belts and zones. So the white stripes are called zones, and the dark stripes are called belts. And what these actually are different cloud layers. So the white clouds are actually above the darker clouds lower down in the atmosphere. And so where we're seeing these white clouds is actually air rising, forming new clouds above the darker clouds below. And at the boundaries of these stripes, we have what we call jet streams, which are really fast moving currents of air at the boundaries of warm and cold air masses. We have them on Earth. In fact, the jet stream, you may have heard of meteorologists talking about the location of the jet stream, or the positioning of the jet stream in reference to weather. It's really important in driving weather here in North Carolina, where the jet stream is. So we have one important one on Earth. Jupiter has like 8. And that results from Jupiter's day being about 8 or 9 hours long. So Jupiter spins really fast. And that's what causes all these stripes, is the physics of Jupiter spinning really fast causes these warm and cold air masses to form, and then jet streams to form at their boundaries, and then we get stripes. So that's Jupiter. There's a lot of fun stuff to talk about with Jupiter that I won't get to for the sake of time, but if we come up here to the poles, we can see the colors change a little bit. We see a lot of different cyclones, which are just basically hurricanes at the poles. And there are a lot of really interesting things that happen at the poles that we're still researching, actually. We have a spacecraft at Jupiter right now called Juno that's taking a lot of pictures of Jupiter and trying to figure out what's going on in the atmosphere. So stay tuned for a lot of really cool science coming out of that mission. But for now, I'll move to our next location in our tour of the giant planets, which is Saturn. So as we head over, probably the most famous thing about Saturn, obviously, is the rings. So I think I saw some people talking about rings in the chat earlier. Definitely, Saturn is the crown jewel of the solar system. It is beautiful. Just the rings and the yellowy color, it's beautiful. So we can go ahead and talk about the rings. So the rings actually are not continuous objects. They are an uncountable number of particles, and they are mostly water particles. I should say ice particles, frozen water, because liquid water can't really exist out this far. But the rings are mostly water, which is really interesting to think about, that this far out in the solar system, 99.9% of the rings are composed of water. And water, of course, being a really important factor for life, sometimes begs the question, could we use the water in the rings or anything like that? Could life exist there? And short answer is probably not. But yeah, for now, I'll just talk about the rings. So the rings probably formed from, we think, moons. So there's a certain point when planets are forming, there's a certain point because of gravity close to the planet where moons can't exist. If a moon were to exist there, it would be torn apart by the force of the planet's gravity. So we think that's part of why rings exist, is objects move too close to the planet, and we end up with those objects being torn apart into pieces, and we get rings. So the rings are labeled going out from the farthest ring inwards, at least in the main set of rings. So this thin ring on the very outside, I'll try to paint over, this very thin ring is called the F ring. But aside from that, these inner rings are labeled A through D, going out to in, and they're labeled by color. So this outer ring goes from this little gap here, which is called the Cassini division, named for the scientist Cassini who discovered it. Cassini was also the name of the spacecraft that most recently studied Saturn. So Cassini was a very important scientist when it comes to Saturn. So from this gap out is the A ring. And then this darker ring here is the B ring. And then this lighter colored ring here is the C ring. and then the innermost ring is the D ring. And there are a lot of different rings actually that we can't see. So for instance, there's a ring called the Phoebe ring, which is called the Phoebe ring because of Saturn's moon Phoebe. Between Saturn and Phoebe's gravity, they can pull material in and form a ring. So that physics also explains some of the gaps in the ring. So this outermost gap is called the Encke gap, and then this, of course, the Cassini division. The Cassini division was also caused by a moon. It was caused by a moon called Mimas. So a lot of the physics we see with these rings are actually caused by moons. The rings themselves are about 300,000 kilometers across, which is, I believe, like 20 Earths could fit across them. So a lot, they're huge. But despite that, Saturn entirely could fit in Jupiter along with all the other planets. So just for some context about how big Jupiter is.
So Caleb,
Yeah.
Matthew has a question. Since you mentioned that the rings are like 99 point whatever water particles, why are they such different colors?
That's a great question. I don't know the answer to it off the top of my head. There is the composition of the rings. It may have to do with the thickness or the density of material there. There are a lot of factors that play into what all the colors are. There's also a ton of material. So even though it's 99.9% water ice, there is also a lot of dust. So I'm not entirely sure. That may actually be a better question or Dr. Smith may be able to answer that question a little better than I can. But that's a great question, and I would encourage you to look into it. But for now, if there are no other questions, I'll just mention one more cool thing about the rings, which is how thin they are. So if we look at the rings side on, we can see they kind of disappear, like almost completely disappear. And that's because the rings are, I would say, paper thin, but they're a lot thinner than paper. So the rings can be anywhere from 10 meters thick to 1,000, or 10 meters thick to a football field thick, which is 100 meters. So they're incredibly thin. To scale, they're anywhere from 100 to 10,000 times thinner than a piece of paper, depending on the location of the rings. There's some variation in the thickness. So when we're referring to things that are super thin, maybe instead of paper thin, we could say Saturn's rings thin. I would love to make that a thing.
Maybe a little bit more of a mouthful.
Yeah, maybe a little bit. So moving from the rings, there's one more cool thing I want to touch on with Saturn. If we move up to the North Pole, we'll see something that we don't see a lot on planets. Like if we're looking at Earth, we never see this. There's a hexagon. So normally when we're looking at planets, we see circles. So on Jupiter, the Great Red Spot was an oval. Oval BA was an oval. All those other ovals. Most storms on Earth we see are similar. They're not perfectly circular, but a lot of times they're at least curved. We don't see polygons. So we really have never seen, we don't see things like this very often. So there is a hexagonal storm at Saturn's North Pole. And this is actively being studied. We first saw it with the Voyager missions in the 70s and 80s. And then Saturn's North Pole was permanently on the night side of Saturn until the early 2000s when we sent Cassini. And then the North Pole came into view again, and we saw this hexagon. And so, as I mentioned, it's actively being studied. The leading theory about why this happens, at least right now, was published in September. So this is very new science. So what we think is going on here, there is, as I mentioned with Jupiter, there are jet streams on Saturn too. And there's a jet stream around the North Pole of Saturn. And we think there's a storm in the middle, and then there's a jet stream around resulting from that storm. And then that storm causes friction in the air lower down. And then that spawns other storms. And then those storms squeeze the original one into a shape. So you can imagine this would be a circle. But then if you took 6 other storms and squeezed them in on the circle, it would kind of make 6 sides, and you could get a hexagon. So this has been produced in fluids because gas is a fluid. We can test it in other things like water, and we've shown that this can happen. So that's what we think might be going on here, which is pretty cool, that there can just be a hexagon on another planet. And for context of the size, each side of the hexagon is about 1 Earth long. So this is a huge feature. So you can imagine 6 Earths all going around the North Pole of Saturn, and that's kind of what that is. And the last thing I'll say about Saturn is it could float. So if you put Saturn in a bathtub, it'd have to be a really huge bathtub, and you'd kind of have to ignore gravity a little bit. But if you were able to put Saturn in a really huge bathtub, it would float. Saturn is mostly made of hydrogen, which is the lightest element. So Saturn's density is really low, significantly lower than water. So if you were to put it in water, it would float. So who knows, maybe, I don't know. I just think that's cool. And moving on, if there are no questions.
Before we move on, John wanted to know if Jupiter had the same direction of rotation on its axis as Earth does. And I guess like the other planets, are their rotations similar?
Yes. So that actually leads well into where we're going next. So I'll go ahead and start heading over there. They all spin the same direction, I believe. The exception may be Uranus, which I'll talk about in a second. But at least Jupiter and Saturn, they both spin the same direction Earth does, which is counterclockwise. So there's some really interesting physics about why that happens. But that's a great question.
Yes, and Rachel confirmed that Uranus doesn't, and that that most do because they all evolved from the same disk. Very interesting.
Yeah.
Uranus probably got knocked around a little bit.
Yes. So I'll talk about that a little bit. So this is Uranus. So it is unfortunately the least popular gas giant, or I should say giant planet. It is the 3rd largest, and it doesn't get a lot of attention. Unfortunately, it is probably my favorite, in part because it's ignored, but there's some really cool things that happen on Uranus. It doesn't get that much attention because it looks kind of boring. It's just this pale blue color. And no matter how beautiful it is, if it looks the same, we can just look at Jupiter and see all this crazy stuff happening. And, it's just, fascinating. But what's interesting about Uranus, so this deep blue color happens because of methane. So methane is, it's a gas, it's a greenhouse gas. On Earth, we worry about methane sometimes because of its impacts on climate change and global warming. But it is responsible for the blue color of both Uranus and Neptune. So most of Uranus and Neptune, again, are hydrogen, but Uranus and Neptune both have higher concentrations of methane, and that's why they're blue. And Uranus is uniquely almost entirely blue. Except for this one cloud feature. There's another cloud feature on the other side that looks similar. But this cloud feature is actually indicative of what we were talking about earlier with the axis and the tilts and the direction that they spin. So this cloud is a feature resulting from a storm at Uranus's North Pole. So I'm going to zoom out really quick and do something very cool with OpenSpace. So we can turn on the trails. So all these trails are moons. So we can see all of these moons orbiting around Uranus, and they orbit around Uranus's equator. So if we look at it side on, we can see, so this is where the equator is. But on Earth, the shadow, what we call the terminator, which is one of the coolest names in astronomy, the point where it goes from the day side to the night side, is vertical compared to the equator. That's not true on Uranus. So if we were to follow the shadow, this is what actually Uranus looks like. So I'm going to zoom out a little bit and speed up time. And we can see all of these moons going around Uranus. And if we look at the North Pole is facing almost directly towards the sun. So the sun is, let's see, over there. And Uranus is facing, the North Pole is pretty much facing directly towards the sun, which results from Uranus's orbit, or I should say Uranus's tilt is over 90 degrees. So it lays on its side. Probably it got hit really hard by something, as Dr. Smith mentioned. It could have been hit really hard by something really huge and just fallen on its side and all of its moons. And Uranus also has rings, as we saw in the picture on the first slide that we were looking at. But they're all on their side, which is really cool. And that is what causes this storm at the North Pole. So when the North Pole is facing the sun all the time, of course, the sun is going to be warmer. And when there's warmth, there's wind that moves to cool it down. And when all of that wind goes to the North Pole, it meets. And then when it meets, like two waves crashing into each other, it goes up, it forms some clouds, and you get a storm. And so that's what's happening on Uranus. There's this North Polar storm that's causing these thin cloud features lower down. And that all happens because it got hit really hard by something. And that's one of the cool things about astronomy is you never know. There's so many just crazy things that can happen that cause really unique features. And the last thing I'll mention with Uranus is something we touched on earlier. Uranus has a moon named Miranda, which of course is the name of one of our hosts today, but also the name of a Shakespeare character. And that's true of every moon except 3 that Uranus has. They are all named after Shakespeare characters. So I can pull up the list of moons over here on the side. We go to planets, Uranus, moons. Let's see. So there's Belinda, Bianca, Cordelia, Cressida, Cupid, Desdemona, Juliet, Mab, Ophelia, Perdita, Portia, Puck, Rosalind. These are all Shakespeare characters, which is just one of the many cool signs that we scientists are great at naming things. So the last place I'll go.
So before you move off of this, we did have a question earlier about how many moons each of these giant planets have. So can you give us a specific number?
Yes. So I think I saw a little bit of controversy in the chat earlier. So to clear that up, there are 27 moons around Uranus. And then there are, I have it written down so I don't forget, there are 79 moons around Jupiter, 82 around Saturn, and 14 around Neptune. And so those moons, I could talk for hours about all those moons. There are so many cool moons in our solar system. I mentioned methane earlier. There's one other place in the solar system where liquid exists on the surface of a planet or a moon. And that liquid is methane, and it's on Titan, which is a moon of Saturn. So just a cool fun fact about methane. But the last place we'll go is the smallest, the smallest giant planet. It is the closest to Earth size, although many Earths could fit inside Neptune. And again, we see Neptune has this blue color. And we don't know exactly why Neptune is a different blue color than Uranus. We know that the blue color results from the methane in the atmosphere. We can look at an atmosphere, see what color it is. Certain gases absorb different colors of light and reflect different colors of light. Methane absorbs a lot of red light, reflects a lot of blue light. So it would make sense that they would be the same color if it's the same chemical that's causing the color. But they're slightly different shades of blue, and we don't really know why. One of the many interesting things that researchers are looking into. But Neptune does have a few more interesting features than Uranus does, at least discrete features in the atmosphere. So the obvious one is this dark spot. And again, scientists are the best at naming things. This is a great dark spot. So great dark spots are slightly different from the great red spot on Jupiter. I should also mention Saturn has great white spots, which are a little bit different. But these are a little bit, there are some different things that go into these great dark spots. So they aren't 400 years old. So this great dark spot we saw with Voyager, Voyager 2, which is the only satellite we've sent to see Neptune. When we sent Voyager 2, we saw 2 of these great dark spots. And then when we pointed the Hubble Space Telescope at Neptune again later, we didn't see great dark spots in the same location, but we did see other ones in different places. So these are like storms on Earth, they come and go. And like I said, they are storms, and they are the location in the solar system where we have seen the fastest winds. So the fastest winds ever clocked in the solar system were 1,300 miles an hour, which is like 10 times greater than a Category 5 hurricane. And we saw it in one of these great dark spots on Neptune. So the physics of these storms is really interesting. And I should have mentioned this before with Uranus too. The white clouds are the same, or similar. They're made of the same stuff, methane ice. So when you get ice particles of methane, you get white clouds. And so we see a few of those around the dark spot on Neptune. So they come and go. We see them. A new one pops up every like 4 to 6 years. So we saw 2 with Voyager, and then we've seen 4 since then. And so this one, the one we're looking at now, isn't there anymore. But there is one on Neptune now that's about the size of the Atlantic Ocean. So just for some context on the size of these things, they are huge. And then I'll finish up with, I think, the most fun fact about any planet that we've ever observed. So methane keeps coming back to methane. Methane is a molecule made of carbon and hydrogen. And we think in the pressure and temperature conditions of giant planets like this, there's enough pressure to break molecules apart. So then we could get carbon on its own and hydrogen on its own. And then if that can happen, then you could get carbons pressing together. And the most common or the most famous thing that happens when you get carbon pressing together is diamond. So we think it's possible that in Neptune, as well as Uranus, we could be getting diamonds forming in the atmosphere of these planets. So these could be diamond generating machines. And then if they do make diamonds, then those diamonds would fall and you would have diamond rain. It is also possible that deep inside these planets, the interiors that we don't know about very much, there could be a diamond ocean in which diamond birds float around, which is all the more reason to go and learn more about Uranus and Neptune, because we've only ever sent one satellite to them. And I'll just finish up by saying these giant planets are all really interesting, and they're all very different from each other. And there are a lot of questions that we don't know the answer to. But in addition to that, just these 4 planets, imagine all of the planets that could be like this. All planets that could be giant planets that are mostly atmosphere, that could have really interesting things going on in their atmospheres, over 1,000 mile per hour winds, 400-year-long storms, all of these really interesting things that we can't observe yet. So that we've seen like 4,000 exoplanets, planets that orbit other stars. And a lot of them are planets like this, like Jupiter, Neptune, Saturn, Uranus-sized planets. And there's so many cool things that could be happening on those planets that we don't know about, which is all the more reason to get into science, because that is a direction that astronomy is going over the next many decades. So with that, thank you all for listening, and I'll head back to Earth unless anyone wants to go somewhere else for questions.
All right, thank you so much. So before we get started on Q&A, we do have a special survey for the presentations that are using OpenSpace, and I'm posting it right here in the chat. So if you wouldn't mind, getting feedback is really important for a lot of reasons. So if you could go to that survey and fill it out for us about this program, we would really appreciate it. So Caleb, we do have a few questions from our guests, and if you have any more questions, just throw them in the chat and we will try to get to them. So someone asked about how the moons of the giant planets are defined, or moons in general. What makes a moon from just a kind of body floating around in space?
Right. Yeah. So a moon needs to orbit a planet, first of all. So the difference between moons and planets is actually, it's space objects, the differences between them are kind of blurry. So the moons around the giant planets, they all orbit giant planets, first of all. If they orbited the sun, they might be asteroids, although I don't know that we have any like moon-sized objects that are asteroids, although they may be dwarf planets. There's some complicated categorization, but so pretty much any object that orbits a giant planet that isn't so-called a ring would be classified as a moon. So.
Awesome. And is the reason why the giant planets have so many moons and we only have one just because of their size?
Yeah, so probably it has to do with their size. They can attract more objects that then can orbit around them. So that would be a good explanation of that, probably, yeah.
And someone asked about the kind of how long a day on Uranus would be. Can you tell us the length of like what a day would be on all of the giant planets? Like, since they're so far much further out, right, from the sun than Earth is.
Right. Yeah. So a day on Jupiter is about 8 or 9 hours. That is the only one I know off the top of my head how long a day is. I do know the length of the years for a lot of these other ones. So Uranus's year is 80 years long. So, which the other planets have seasons like we do. So the Uranian seasons are 20 years long. And then Neptune is, I believe, over 100 years. Saturn is something like 30 years. long. So the years are super long. I believe I would have to look into. That's definitely a question that you could find on Google, is how long the days are on the other planets, but I don't know off the top of my
Day
head.
is the rotation of the planet versus the year is like literally how long it takes to make it.
Right. Yeah.
That's crazy.
Yeah. So that actually has interesting
perspective of like space is just it blows my mind.
Right.
Hear about it. So
yeah. So that actually has interesting implications for the weather on other planets, is how long the seasons are and how long the days are. As I mentioned with Jupiter, the fact that the day is really short is what causes the stripes. And then on Uranus, the fact that the North Pole is pointed directly at the sun for like 20 years means a storm can form there. So there's some really interesting things, that implications that has.
awesome. Let's see. And so I found it interesting when we were talking about Uranus and its weird tilt that, you know, Rachel and you mentioned that it was that it probably got hit by something else. But these are gas giants. And so I would imagine if, you know, I think of hitting something, if it's surrounded by gas, then the gas just kind of flies everywhere. But so can you tell me a little bit about how like you hit something that is like mostly made of gas?
Yeah, so that's an interesting question. So it's not, I guess, hitting a solid, like you know, if you were to like smack your hand on a wall, it would stop. You might be able to push on something and move it. But with a gas, it's a little bit different, or I should say with fluids. So like if you're jumping into a swimming pool, you're displacing a lot of water as you move through it. And it's kind of the same thing if you were to hit a gas giant. So say like a moon-sized object flew into Uranus, it would carry a lot of the gas with it. And because of that, it could still pull, both from gravity and from friction, it could still pull on the planet. So it's a little bit different, but it can still, I should also say the interiors of these giant planets aren't all gas. So eventually the gas gets compressed into liquid or superfluid. We think that there may actually be like solid metallic hydrogen at the core of some of these things. And so they do have some like non-gas in them that could also play a role. But that's a great question.
Yeah, and so Rachel is commenting as well in the chat that hitting gas can have a huge impact. Think meteors coming through our atmosphere.
Yeah.
And also think, I'll just add, there was a comet. So even hitting Jupiter has a huge gravitational pull, so it can pull in objects that effectively smash into the gas. And so comet Shoemaker-Levy that hit in the 1990s even left scars, like quote unquote scars, on the surface of the planet for a period of time that eventually went away. I don't think we can see that anymore in the data. Is that right, Caleb? Did you see any remnants of the scars from Shoemaker? I think those are gone for now.
Yeah, I'm not entirely sure. I wouldn't know for sure how to identify it.
Right, because that's something you could
actually,
you can look up, you can see it pulls apart the Jupiter itself, pulled apart the comet, but when it hits like a brick wall, right? Yeah. So when you see these meteors coming through, the light you see is the sort of the burning up of or melting of the outer layer of a piece of an asteroid. And so this impact can actually be pretty significant, but it's a little counterintuitive, like Miranda is saying, that we couldn't live on the surface of these gas giants because there's no surface, but yet objects can hit these surfaces and explode and have an impact and fall through.
Yeah, I think it just it's just so interesting. I guess it speaks kind of the gravity of the core of the planet, and just like I don't know.
Yeah, I don't know. And Caleb may have mentioned Jupiter is almost the size of a star, so it almost became a brown dwarf. It was almost the size of a brown dwarf, a small star. And so if that had happened, if Jupiter had formed to become a star, our entire solar system would be certainly very different. So it's pretty big.
Very cool. And I actually had a question, and I'm sorry if I missed it, Caleb, when we were when you were talking about Saturn's rings, did they all form at the same time, or are they kind of being constantly added to, or, you know, if a plant, you know, something kind of breaks up near Saturn's surface into tiny pieces, could another ring form?
Yeah, so they probably all formed like over a period of time. Like I don't think if you collected all of that mass and put it into one object, it'd probably be a pretty big object. So I think it was probably a combination of things over a long time. So I guess in theory you could, you know, if you had one of Saturn's moons fell within a certain point, it could be torn apart and you could get more material. But I don't think it would be. We would never see something that would cause a like super noticeable difference in the appearance of the rings, I don't think.
Great, and we are running short on time, and I don't see any other big questions. We are posting some links in the chat. I'm going to post that survey to OpenSpace, the OpenSpace survey again. Again, if you can fill that out for us, we'd really appreciate it. And thank you so much, Caleb, for being here and showing us this amazing presentation. I know the more I learn about kind of all the questions we still have, the more I am excited about what is coming in the future with space exploration and science in general. And I know I always learn something every time I hear Dr. Smith give a presentation. So definitely check out the presentation that she's giving tomorrow on the terrestrial planets and other objects in our solar system using OpenSpace. It's going to be fantastic. And I think Carrie might have posted it in the chat earlier. Maybe she can post it again. You can sign up for that tomorrow. And with that, let me pull it slide.
Great job, Caleb. I think it's a fascinating tour. Thank you for doing that.
Yeah, thank you all for coming and listening.
All right, and thank you. Yeah, thank you all for coming. I want to thank NC Space Grant for sponsoring Astronomy Days, including our captioning. And if you want to get some Astronomy Days gear, head over to the museum store at store.naturalsciences.org. You can pick up an awesome zip hoodie or a t-shirt. I am definitely getting that zip hoodie. My one from last year is my favorite. And if you're a member, thank you so much. Members of the museum help contribute to so many programs, including this one. And you also get some really cool discounts at the museum and some great programs that are exclusive to you. So you can check that out on our website. And thank you again so much for coming. We hope to see you at more programs during Astronomy Days today and tomorrow. And we have recordings available of all the ones that you may have missed on our website as well. Thank you so much, and we'll see you next time.